During an SN2 reaction, a good leaving group is displaced from an unhindered carbon by the attack of a strong nucleophile. Good leaving groups include halides and sulfonates, such as a tosylate, a mesylate, or a triflate. SN2 stands for second-order nucleophilic substitution. The rate-determining step mechanistically involves both the substrate as well as the strong nucleophile. Therefore, the rate of the reaction depends on the concentration of both of these species, making it a second-order process. Many strong nucleophiles are negatively charged. However, some can be neutral, in which case one additional mechanistic step would be needed. During that additional mechanistic step, a proton would be lost to neutralize the product. SN2 reactions do not occur on tertiary centers because they are too hindered to allow the nucleophile to approach. On the other hand, secondary centers can undergo SN2 reaction, as shown in the following example, where methoxide attacks this secondary carbon of the substrate, displacing the iodide leaving group. As we mentioned earlier, when the strong nucleophile happens to be neutral, as it is here, an additional mechanistic step is needed at the end of the reaction. This step entails the loss of a proton from that nucleophile so as to neutralize the final product. The example below was seen earlier, but with unspecified stereochemistry. Since this center is a stereo center, stereochemistry of the product is a concern. In SN2 reaction, the attack of the nucleophile occurs directly opposite the leaving group. This results in inversion of configuration of the center undergoing the reaction. In summary, SN2 reaction is a concerted process during which the nucleophile attacks at the same time as the leaving group is lost. This necessitates an unhindered electrophilic carbon, meaning that the electrophilic carbon should be methyl, primary, or secondary. A strong nucleophile is also needed. Strong nucleophiles include anions other than fluoride, polarizable species such as hydrogen sulfide or thiols, or electron-releasing neutral species such as ammonia or amines. The concerted nature of the SN2 reaction has some consequences. One is that the configuration of the reactive center is inverted. It's useful to compare this result to the SM1 reaction, in which the configuration of the reactive center is racemized instead. The absence of a carbocation intermediate in SN2 reactions means that no carbocation rearrangement will be possible. This is also in direct contrast to the SM1 reaction, which can have carbocation rearrangements. The preceding description of the SN2 reaction was an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.